For roots and radicals, the first one, if a is equal to 5 root 2 and 2a is equal to root 2x, what is the value of x? It's part of the other problem. We'll cover it up. The first thing we do is we substitute. We take what a is equal to and we replace it in the other part of the problem. Now we multiply. 2 times 5 gives us 10. We don't change what's underneath the radical. It's almost like how you would treat a variable. You multiply the coefficients, but you don't change the radical. Excuse me. If I want to put 10 back underneath the radical, I need to square it. And what this does is it sets up a scenario where the square root of 2 times 100 is equal to the square root of 2 times some number. The only scenario where this is true is if 100 is equal to x. For this next problem, they tell us that 2k squared plus 17 minus x is equal to 0. And we can plug in our x value. We get root 2k squared plus 17 minus 7 is equal to 0. The first thing we want to do is get this radical all by itself so we can square it to cancel out. We'll add 7 to both sides to make this happen. So now we square both sides. On the left, the square root and the square cancel each other out, and we're left with what's underneath the radical. Nothing changes. On the right, 7 times 7 gives us 49. We subtract 17 from both sides. This gives us 2k squared is equal to 32. From here we divide by 2 on both sides. We get k squared is equal to 16. And just how earlier we canceled out a square root by squaring, we cancel out a square by square rooting. I think that's a verb. So k is equal to either a positive or a negative 4. You may recall earlier in the problem they told us that k has to be greater than 0. So that only leaves 4 as a possible answer because negative 4 is not greater than 0. So down here in the bottom left, we could graph this, but we don't need to because we know that we have a system of equations. Y is equal to x minus 11 squared and y is equal to 25. We can take y and what they're equal to and replace. So this gives us 25 is equal to x minus 11 squared. To cancel this out, we could expand x minus 11 by squaring it using the area model. It's going to make this problem a little more complicated. The faster method is probably to cancel out this square by square rooting both sides. On the left we'll have a plus or minus 5, and the right will have x minus 11. So just like absolute value problems, this one splits. We have the positive side and the negative side. On the left here, we'll take positive 5 is equal to x minus 11, and the right, negative 5 is equal to x minus 11. The steps are the same for both sides. We add 11, and we get 16 is equal to x, or we get 6 is equal to x. Now keep in mind that we're looking at the intersection of two lines, and one of those lines is y is equal to 25. So if we consider these as coordinates, the y value has to be 25. What we're looking for is the distance between these 2 points of intersection. The y value is the same, the only difference is the x. We take 16 minus 6, which gives us 10. If we wanted to see what this looked like graphically, here's our line y is equal to 25, and here's our line or our parabola I should say, y is equal to x minus 11 squared. They cross here at 2 points, 625 and 1625. So our answer 10 represents the distance between these 2 points of intersection, but you didn't have to graph it. Next problem here in the top right, we see that the square root of x minus a is equal to x minus 4. And they tell us that a is equal to 2. We substitute a for 2. To cancel this out, we're going to square both sides. On the left, this just gives us x minus 2. On the right, we have to square this entire quantity, which I think is the best way to do this is to use the area model, or the box method. We multiply rows and columns, and we get this. We simplify, and all of this is set equal to our x minus 2 from earlier. We'll add 2 to both sides. We get x is equal to x squared minus 8x plus 18. And from here we can subtract x from both sides, and we get 0 is equal to x squared minus 9x plus 18. So if we factor this, we're looking for factors of 18 that add up to negative 9. Turns out those two numbers, negative 6 times negative 3, and negative 6 plus negative 3. So we can write this out as x minus 6 and x minus 3. There are two solutions that will make this equal to 0, a positive 6 and a positive 3. For the bottom right, if we want to replace x with 9, this problem becomes the square root of k plus 2 minus 9 is equal to 0. We want to isolate the radical by adding 9 to both sides, and we're left with the square root of k plus 2 is equal to 9. To cancel out this radical, we can square both sides. We're left with k plus 2 is equal to 81. We subtract 2 from both sides, and we get 79. On the back, the top left problem, we're going to use this formula here. 9 raised to the third fourth is the same thing as the fourth root of 9 cubed. If we had a calculator, this would be pretty straightforward. Easy problem to enter in. The problem is we don't. So if we want to simplify this, instead of taking the fourth root all at once, we can take the square root, which is part of it. And this brings our 9 to a 3. And if you know anything about square roots, this is the identical thing as root 3 to the third power. All square roots have this too. It's kind of like the invisible 1 in front of x's. What is 3 to the third power? Turns out is 3 times 3 is 9 times 3 is 27. If we change this to 9 times 3, we can pull out the square root of 9. What is the square root of 9? It's 3. What's left underneath the radical? Root 3. In the bottom left, we have the square root of x plus 3 is equal to 8. That's the solution to the square root of 9 and the square root of 64. We could do plus or minus, but in this case it won't matter. You're going to get the same answer either way. We know that the square root of x is equal to 5. When we square both sides, we get x is equal to 25. The last problem, you don't even need to solve it. We're just going to use that same formula. This becomes the cube root of a squared. And that's it.